The headlines were dramatic, almost cinematic, hundreds of earthquakes shaking the deep, dark abyss. Not just one or two, but a swarm of over 300 tremors registered in a single day. The source wasn't a familiar fault line on land, not the San Andreas or some other terrestrial troublemaker. No, this seismic symphony was playing out far from human eyes, beneath the crushing pressure of the Pacific Ocean. The culprit was a volcano, an immense mountain of fire hidden from the sun, known to scientists as Axial Seamount. It was stirring from its slumber, and its restless movement sent shockwaves rippling through the seafloor. So, what exactly is this behemoth making all the noise? Axial seamount is an underwater volcano, a type of geological feature known as a seamount. Think of it as a mountain that grew from the ocean floor, but didn't quite break the surface of the water. It's a colossal structure, rising about 1,100 meters from the surrounding seafloor. Its summit rests roughly 1,400 meters below the waves, a depth where sunlight cannot penetrate. This isn't just any underwater mountain, though. Axial is one of the most active and intensely studied submarine volcanoes in the entire world, a title it earns through its frequent and predictable eruptive cycles. Its name, Axial, comes from its unique position. It sits directly on the axis or the center line of an underwater mountain range called the Juan de Fuca Ridge. This ridge is a mid-ocean ridge, a place where two of Earth's tectonic plates are slowly pulling apart. Magma from the Earth's mantle rushes up to fill this void, solidifying into new oceanic crust. Axial Seamount is located right over a hotspot on this ridge, a particularly robust plume of magma, which makes it far more volcanically active than the rest of the ridge system. In 2014, scientists completed the installation of the Cabled Array, a component of the Ocean Observatory's initiative. This incredible feat of engineering connected the volcano directly to the internet with a network of high-tech sensors, cameras, and instruments via a fiber optic cable stretching to the Oregon coast. For the first time, scientists could watch an underwater volcano in real time 24/7. To understand Axial, you must first appreciate its home, the Juan de Fuca Ridge. This isn't just a random chain of underwater hills, it's a fundamental planetary boundary. The ridge is a spreading center, a place where new Earth is born. Here, the Pacific Plate moves westward and the Juan de Fuca Plate moves eastward. This slow, inexorable separation stretches the oceanic crust thin, like taffy being pulled apart. The pressure release allows superheated rock from the mantle below to melt and rise as magma. Magma erupts onto the seafloor and cools in frigid ocean water, forming fresh crust in the form of pillow lavas and sheet flows. This process of seafloor spreading is happening all over the globe along a 65,000-kilometer-long network of mid-ocean ridges, the largest single volcanic feature on Earth. The Juan de Fuca Ridge is a relatively small segment of this global system, located just a few hundred miles off the coast of Washington and Oregon. Its proximity to land and the intense scientific interest it garners make it one of the most important spreading centers for study. It is the engine that drives much of the geology of the Pacific Northwest, including the notorious Cascadia subduction zone. The volcano's summit is marked by a large rectangular caldera, roughly 3 by 8 kilometers in size. This caldera formed when the roof of an underground magma chamber collapsed after a massive eruption emptied it out. The caldera's walls are defined by faults, the very places where most seismic activity occurs as magma forces open fractures. So why did over 300 earthquakes suddenly rattle Axial Seamount? The answer lies deep within the volcano's plumbing system. These were not the kind of massive, plate-shifting earthquakes that level cities. Instead, they were small, rapid-fire tremors that signal the movement of magma. Molten rock ascends from the mantle into the magma chamber a few kilometers beneath the caldera floor. It pushes the surrounding rock aside. The crust is cold and brittle. It cracks. Each crack releases a small burst of energy we detect as an earthquake. An earthquake swarm is the acoustic signature of a volcano getting ready to erupt. It's the sound of the magma chamber inflating. Scientists monitor Axial with seismometers, tilt meters, and pressure sensors. As magma fills the chamber, the ground above bulges upward and outward. Axial's cabled observatory data showed the caldera floor rising by several meters over months and years. The quake swarm is the final, frantic phase of inflation. The chamber is full and pressure is critical. Daily quakes can jump from a handful to hundreds to thousands in the final hours or days before lava breaks the seafloor. This is what happened before Axial's eruptions in 1998, 2011, and 2015. 2015 was a landmark. The first underwater eruption forecast with such accuracy thanks to real-time observatory data. Each of Axial Seamount's eruptions has been a chapter in a continuing story, teaching scientists more about the secret life of underwater volcanoes. The 1998 eruption was the first detected near real-time using remote hydrophones, underwater microphones that picked up seismic rumbles. When researchers arrived by ship weeks later, they found a brand new lava flow over 9 kilometers long. The water above the flow was still warm and cloudy with chemicals. New deep-sea communities were already colonizing the fresh glassy rock. The 2011 eruption was even more enlightening. Scientists had placed autonomous monitoring instruments on the summit. Retrieved data showed the seafloor subsided about 2.4 meters, documenting an inflation-deflation cycle. Then came the 2015 eruption, a watershed moment. With the cabled array, scientists watched the eruption live on their screens. They tracked thousands of tremors migrating from the central caldera toward the northern flank. Then they knew an eruption was underway. ROV surveys later mapped flows covering about 19 square kilometers, captured pillow lavas and vast sheets of glassy rock, and discovered new hydrothermal vent fields. With Axial Seamount now reinflating and rumbling once more, the question on everyone's mind is, what will the next eruption look like? Based on its past behavior, the pattern is pretty predictable. The volcano will continue its slow, steady swelling for several years. The caldera floor will rise. The number of small earthquakes will gradually increase. Then, without much warning beyond a few days, a massive earthquake swarm will begin. That swarm signals magma is on the move. An eruption is imminent. Lava will likely erupt from fissures within the caldera and along the volcano's flanks, following the path of least resistance. The eruption itself will be a silent, hidden spectacle. At a depth of 1,400 meters, water pressure suppresses explosive activity. There will be no fiery fountains or ash clouds like a terrestrial volcano. Instead, the eruption will be effusive. Lava will pour out onto the seafloor, forming pillow basalts and sheet flows. The lava can exceed 1,200 degrees Celsius, about 2,200 degrees Fahrenheit. That heat will flash boil surrounding seawater, creating a megaplume. A massive, swirling cloud of superheated, chemical-rich water will rise hundreds of meters through the water column, but it will not reach the surface. What does this mean for the West Coast? The direct physical impact will be localized to the volcano, no direct threat to shipping, and Axial's effusive style makes it an exceedingly poor tsunami generator. The megaplume will inject heat, iron, sulfur, and other chemicals into the ocean, a massive fertilization event. This can trigger phytoplankton blooms that cascade through the marine food web. For scientists, the next eruption is a golden opportunity. ROVs and AUVs will be ready to study fresh lava, new hydrothermal vents, and the biological communities that spring to life. They'll be ready the moment the eruption is confirmed. Assessing the real dangers. When headlines speak of hundreds of earthquakes and an awakening underwater volcano, it's natural to feel a sense of alarm. However, for people living on the West Coast, Axial Seamount poses virtually no direct threat. The seismic activity, while dramatic in number, involves very small magnitude earthquakes, the cracking of rock on a local scale. Large tsunamis are caused by sudden vertical displacement of massive volumes of water, typically from subduction zone earthquakes or massive landslides, not from Axial's slow, effusive eruptions. The danger in the Pacific Northwest comes from the Cascadia Fault, not the Axial Seamount volcano. For ships, the answer is a clear no. The eruption occurs nearly a mile deep and its effects dissipate long before reaching the surface. For marine life, the story is more complex. An eruption is destructive and creative, sterilizing lava-covered areas, but creating ecological oases around new hydrothermal vents. Slow-moving organisms like sea cucumbers or starfish in the lava's path are buried, but hydrothermal vents then support chemosynthetic communities. These vents are oases in the deep-sea desert. Bacterial mats, tube worms, crabs and fish rapidly colonize using chemosynthesis as the base of a new food web. For scientists, the greatest danger is our ignorance. Every eruption is a lesson that forces us to learn more about the planet. So while headlines can alarm, the real story is one of science and renewal, not imminent coastal danger from Axial. Axial is the best monitored underwater volcano, but it is far from alone, part of a vast global family of submarine volcanoes. Some volcanoes, like Kilauea and Mauna Loa, form over hotspots. Iceland is a ridge hotspot hybrid. Hunga Tonga shows what shallow explosive interactions can do. Loihi is the next Hawaiian island in the making. Axial is the benchmark, a revolution in real-time observation that turns volcanology from a reactive to a predictive science. By listening to its rumbles and watching cycles of renewal, we take the pulse of planet Earth, learning how the forces that shaped our world will shape its future for millennia to come.